I wanted to start this lecture talking about the metamorphic reactions. These are chemical reactions that happen in metamorphic rocks in order to change a rock. So metamorph again means that the rock has changed from an original or precursor rock. So these reactions are what cause those changes. So the first one we refer to as the growth of new minerals, because it is literally the growth of new minerals within the rock. During the heating, increase in temperature, and the pressure that takes place that causes metamorphism, there are chemical reactions that happen between different minerals within the rock, and then also between water, groundwater basically, and minerals within the rock. Normally, water would not react with minerals in this kind of way, but we are talking about increasing the temperature and pressure above 200 degrees C, and at that point, the minerals become more reactive. So this can destroy existing minerals and then create new minerals. It does not happen to all metamorphic rocks. Okay, just some metamorphic rocks experience the growth of new minerals. And down here I've just got an example of a couple of minerals that we've talked about, so you're familiar with them. And this is a very common reaction in metamorphic rocks. Potassium feldspar, which you find a lot in felsic rocks, will react with water and create the hydrous mineral muscovite. So I've got the formulas down here just to remind you. So we've got the potassium here in the feldspar, water here, and then if we look at the formula for muscovite, we can see we've got that potassium and the other elements, the aluminum, silicon, and here's that water, the OH group. So that's a pretty typical reaction that you see in metamorphic rocks, and you'll see that there are actually a lot of micas in metamorphic rocks. So we talked about biotite and muscovite when we talked about minerals, but they are not very important minerals in igneous rocks or sedimentary rocks, but they turn out to be pretty common in metamorphic rocks. The second reaction that happens is recrystallization. So this does happen to all metamorphic rocks. So all metamorphic rocks, when they experience metamorphism, will have the crystals or grains that make up the original rock experience this recrystallization. And what that does is it changes the shape and the size. Often, recrystallization results in larger grain sizes, so you will often see crystals get larger as they go through metamorphism. These are a couple of thin sections, and a thin section is literally a very thin slice of rock that's been cut thin enough so light can look through it. And you're looking at these from under a microscope, so we're seeing individual crystals here. And this is just showing the effects of that recrystallization. So up here in the top we have a quartz sandstone. So we've got a whole bunch of grains of quartz. These are broken pieces of quartz. There's some other stuff in here, probably the mineral epidote, which is pretty common in sedimentary rocks as well. Once a quartz sandstone goes through an episode of metamorphism, it becomes the rock quartzite. So quartzite has then experienced this recrystallization, and we can see that in the texture of the minerals. So up here we have lots of individual grains, and they are surrounded by little tiny crystals that are gluing them together. Right, these are the cement basically that's gluing the quartz grains and the other stuff together. After recrystallization, those tiny grains are gone, because during recrystallization they become incorporated in these larger crystals. So now we have interlocking crystals instead of grains that are cemented together. So that interlocking texture is a result of recrystallization, and we call that a crystalline texture. So igneous rocks had a crystalline texture as well, right? Because the crystals actually grew in a liquid, and therefore they had to grow next to each other. Here we have crystals that have also grown, not in a liquid though, they've just recrystallized in the solid state, individual atoms moving, which makes it a much slower process. Since we don't have the liquid, these are not hot enough to melt, but we end up with that same interlocking crystalline texture. So the main texture that we see in a metamorphic rock is a result of recrystallization. But recrystallization does happen, since it happens to all metamorphic rocks, it can happen under confining pressure only or under the directed pressure. And it turns out that that makes a big difference. If you have recrystallization happen under confining pressure only, and remember that's equal pressure from all directions, then we don't change the shape of the crystals. So no shape change under confining pressure. But when a rock experiences recrystallization when it's under directed pressure, then we do see a shape change in the minerals. So remember, directed pressure is when you have pressure from all directions, but in a couple of directions, that pressure is much larger than in other directions. So when that happens, we do see the crystals responding to that change in pressure as they recrystallize, and we get a shape change, and that shape change is basically what we see in the rock later as the main texture in rocks that have experienced directed pressure. So this graphic is just showing that shape change. So here we have a fairly circular mineral grain, and it's going to be put under directed pressure. The pressure is coming from the top and the bottom. So how do we know that? We know that because that's the way the mineral looks like it's been squished. It hasn't literally been squished. Instead, what has happened is that parts of the mineral, so this part of the mineral here and this part of the mineral here, the individual atoms have moved and recrystallized on the ends, on both sides. And that gives us this elongated mineral. So this is the new extra parts of the mineral that have been created during that recrystallization under this directed pressure. So you can think of the atoms as moving from a place of high pressure to a place of low pressure. So again, if we look at the top figure, if this is the direction in which this rock is feeling pressure, additional pressure from the directed pressure, then the minerals up here are under extra pressure, and that makes them unhappy, and that's why they move to these ends where it's lower pressure. And then we end up with this elongated shape. This is a thin section showing a rock that has developed this kind of texture. And one of the things you notice here is that the minerals are all elongated, but they're also all aligned with each other. So we have these really long, thin minerals in here, and they're basically all aligned in the same direction. So we can use this information again to figure out where the directed pressure was coming from. Where was this rock experiencing the highest pressure? Where was it being squeezed? Again, it's going to be perpendicular to the direction of the alignment, because again, atoms here have moved away from here and gone here to be under less pressure. So the higher pressure, those atoms are moving away, and they make the crystal shape become perpendicular to the directed pressure. So perpendicular again means 90 degrees. So we have this pressure here, and this is the direction of the texture, and we have a 90-degree angle here between those two things. So we call that texture foliation. So the texture I've been talking about, that alignment, is referred to as foliation. We say the rocks have a foliated texture. And these are just illustrating that again. So in the top here, we have a bunch of sort of flat little black minerals in the rock. And after the directed pressure, they align. So again, you can see the larger arrows here are indicating that directed pressure. And so therefore the foliation is going to be perpendicular to that direction of directed pressure. This is what the rock looked like. So here we have basically just randomly oriented minerals. And then after the directed pressure, which came from these two sides, we have the alignment of the minerals, the foliation, that is perpendicular to that directed pressure. So there are some minerals that will not change their shape in that way, even if they do experience directed pressure. So the only ones that will have a preferred direction of growth. Two important minerals that don't have a preferred direction of growth are quartz and calcite. Now obviously those have been important minerals in rocks that we've talked about. Quartz is important in quartz sandstone, makes up over 90% of the grains in that rock. And calcite is the main mineral in limestone. Both quartz sandstone and limestone are very common sedimentary rocks, so we should expect to see metamorphic rocks made from them. When we do, though, even if they've been under directed pressure, we won't be able to tell because their minerals will not change shape. This down here is just showing basically what kind of minerals more easily change shape. So if you have a bunch of planar or sheet-shaped minerals, they're going to easily line up in this way. And if you have a bunch of sort of little tube-shaped or linear minerals, they're also going to show foliation pretty easily. But quartz and calcite have this more equant kind of shape when they grow naturally, and so they don't develop that preferred direction of growth, and so they do not show foliation no matter what kind of pressure they experience during metamorphism. We have different names for different kinds of foliation because foliation can look different depending on what kind of minerals have developed in the rock. So there are two terms that your book will use, slaty cleavage and schistosity. I put both of those in the category of mica foliation because this type of foliation happens only to rocks that are made almost entirely of micas. So slaty cleavage is what we call mica foliation when the mica grains are really tiny. And then when you get larger crystals of mica, and that usually happens because metamorphism has brought the rock up to higher temperatures, then we'll get what's called schistosity. It's the same alignment of the micas, and that alignment is shown here, right? It's like pages of a book. You get kind of a nice flat surface here, but on the sides you get all these layers, and you can see those layers in the rocks, and that is an indication of foliation. The second main type of foliation is called a gneissic texture. Again, I tend to refer to it mostly as banding foliation, because what happens with this gneissic texture or banding foliation is that the dark and light minerals tend to segregate into different bands. So basically we get light and dark minerals that separate from each other a little bit. It has to do with the way the minerals change shape and how easy it is for them to develop foliation. But the end result is basically a rock that is sort of striped between dark and light bands of color. So that anytime you see those bands, that is also an indication of foliation. We can also have metamorphic rocks that are non-foliated, right? So there are two ways in which non-foliated rocks can develop. First of all, any rock that experiences only confining pressure. So remember, directed pressure is associated specifically with tectonic events like having two plates collide with each other, where you get that additional directed pressure in the direction of the collision. If you don't have that, if you only have confining pressure, then you're going to end up with non-foliated rocks. The second way is what we talked about with calcite and quartz already. So these are two minerals that won't show alignment. So any rocks made of entirely calcite or entirely quartz, they will experience recrystallization. So if you look carefully, you can see the mineral grains will recrystallize into that interlocking pattern, and the crystals may grow larger, but you will not find any kind of foliation. There will be no alignment of the minerals because they don't change shape. A third texture, which is common, but we're not going to focus on it as much in this class, is called a porphyroblastic texture. And a porphyroblast is basically these large minerals that you're seeing here. So these are usually found in a foliated rock. They're usually found in schists, and schists are a foliated rock. So they don't look foliated because they will not actually change their shape, but they are embedded in a lot of micas that will change their shape. So we're going to go through the metamorphic rocks and name them, and just like with igneous rocks and sedimentary rocks, we use their texture and their composition in order to classify them or put them into groups. So the texture that we're interested in this case is going to be their foliation, whether or not they're foliated, and their grain size. And then we will also look at mineral composition. So all three of those factors play a role in how we identify or name these rocks. We're going to start with all of the foliated metamorphic rocks. So the first one is slate. Slate develops when metamorphic conditions are fairly low temperature. So remember, we have to get up to above 200 degrees C, but slate is one of the first ones to develop at that low temperature. You have to have directed pressure, right, because we have foliation. Anytime you have foliation, you also have directed pressure. It has a fairly fine-grained texture, and that has to do with the low temperatures at which the minerals are recrystallizing. It is made mostly of micas. So the foliation type would be mica foliation or that slaty cleavage. And its parent rock is the rock shale. So remember, shale is a sedimentary rock that is made mostly of clays, and clay is a sheet silicate. Micas are also a sheet silicate, so what happens during metamorphism is that the clay minerals transition and change. They recrystallize, and we get the growth of new minerals because the clays change into micas. Some pictures of slate here. Slate is not a terribly hard rock, but it's harder than the shale, the parent rock. It can come in lots of different colors because shale can come in lots of different colors. They're all usually kind of on the dark side. And you can see what they call that slaty cleavage. In this photograph down here, you can see the way the slate is just naturally breaking off is actually parallel to its foliation. This is the same rock basically that used to be used to make chalkboards. And when you read about, people living on the prairie and how the kids would bring their slate to school, they were literally bringing a piece of slate because it's a very fine textured rock, and so it's smooth and you can write on it with a piece of chalk. The next foliated metamorphic rock is phyllite. I've put some how to pronounce it here because There's a lot of different ways in which these rocks could be pronounced, and so it helps a little bit to have that to help you pronounce it right. The metamorphic conditions here are medium temperature, so we have increased the temperature a bit from creating slate, but still directed pressure because it's foliated. The grain size has increased somewhat because we have increased the temperature. The mineral composition, however, is still mostly micas. The micas have simply grown a little bit larger. Their crystals have grown larger because of the increase in temperature. So the foliation type is still the mica foliation type. We now refer to this as schistosity because we're no longer talking about the rock slate. Again, I don't use this word too much. I tend to focus just on the mica. The parent rock here is shale. Notice that's the same parent rock that we had for slate. So basically, shale can be metamorphosed into slate. If you increase the temperature a bit, it gets metamorphosed into phyllite. The difference between shale and phyllite when you're looking at them is that because of the larger grain size, you no longer have this really smooth, flat texture. Instead, you begin to see kind of a wavy texture, and that's because of this increased grain size. So this is the foliation we're seeing here, right? The minerals are aligned, and that's why we're seeing that kind of texture there. The third metamorphic rock is the schist, and that's where the word schistosity comes from. So we've increased the temperature more, still have directed pressure because we still have a foliated rock, but now our crystals have grown large enough that we consider them coarse-grained. We still have a rock made mostly of mica. It's got that mica foliation. This is the one that can contain those porphyroblasts, those large crystals that did not show foliation, sort of embedded within all the mica. Parent rock here is shale too. So again, we can take shale, we can turn it into slate, heat it up more, it turns into phyllite, heat it up even more, we're up to around 350 degrees here, it turns into schist. Schist is a very shiny rock. It has some of that wavy texture still because of the grain size, but an easy way to remember to identify it is that because the grains on the top here are fairly large, it reflects light well. So schist tends to be rather shiny. So these first three foliated rocks were all basically starting with shale. So we go first from shale to slate, increase the grain size slightly, and we go to phyllite, increase the grain size more, and we go to schist. They all have the same parent rock. They're all made of mica because the parent rock was made of clays. And as you recrystallize those clays and they react with each other, they become another sheet silicate. So it's not a terribly different mineral, but it's a little more stable at these high temperatures. Then finally, we have one last foliated metamorphic rock, and that's the rock gneiss. Metamorphic conditions now, we've moved up to 400, 450 degrees C, high temp, directed pressure because it's foliated. This one is also coarse-grained like the schist was. The mineral composition can vary a lot. Part of that is because the parent rock can vary a lot. And remember, parent rock plays a large role in determining what the minerals are in the metamorphic rock. The foliation type here now is banding. Basically, we have large grain sizes, and we're no longer dealing with a rock that is made mostly of micas. Instead, it can have lots of different minerals in it. And gneisses can be different colors too. You always have the banding, but it's not always sort of this black and white. There's a lot of gneisses with pink minerals in them, yellow minerals in them, so you can see different colors. All right, non-foliated metamorphic rocks. So again, these can form in two ways. Lack of directed pressure, which means only confining pressure. Or if they are made with a mineral with no preferred direction of growth, and those two minerals that we're going to be important in rocks that we're going to talk about are quartz and calcite. So we're starting with the rock marble. In this case, there's no real progression in grain size or anything like there was with the foliated metamorphic rocks. So marble is a rock that comes from limestone. So when limestone is metamorphosed, it turns into marble. Limestone is made pretty much entirely of the mineral calcite. So that means that the mineral composition of marble is also calcite. Calcite's one of those minerals that won't elongate. The metamorphic conditions up here can range from low to high temperature. When you have low temperatures, you tend to have smaller crystals of quartzite. When you have high temperatures, you tend to have larger crystals of quartzite. Confining or directed pressure can be part of the metamorphic conditions. So remember, we can't tell from looking at the marble whether we have confining pressure or directed pressure because the rock will look the same regardless. It will not show any foliation. So limestone was already sort of a crystalline rock, or it had a lot of fossils in it. So recrystallization happens in this rock. We don't have the growth of new minerals because the limestone started out with calcite and the marble ends up with calcite. There simply are no new minerals forming in there. So just recrystallization, which creates the marble. The second non-foliated metamorphic rock is the rock quartzite, and the parent rock for quartzite is quartz sandstone. So again, we start out with quartz and we end up with quartz. So the mineral composition of both rocks, quartz sandstone and quartzite, is quartz. The metamorphic conditions are pretty much the same as those for marble. You can have different temperatures, and again, higher temperatures lead to larger crystals in the quartzite. It can be therefore fine to coarse grained. We have confining or directed pressure. We can't tell which. We would need to look at some other rock in the area to see whether we could get a clue about whether or not there was any directed pressure. In this case, quartz sandstone starts out, remember, as grains cemented together. So recrystallization creates that interlocking texture that we see. So it leads to the interlocking crystalline texture. I want to compare quartzite and marble because visually they can look similar with one big exception. So they're both made of a single mineral. Neither of them shows foliation. And they can both be different colors. We think of marble as white, but that's just the really clean, beautiful marbles that came from some very clean limestone that didn't have any shale mixed in. Remember, these sedimentary rocks are forming at the surface of the earth, so there are often impurities in things like limestone and quartz sandstone. It's not usually pure. So those impurities then affect the colors of the rocks that we see. So limestone can sometimes, you can see bands of shale in it, and after metamorphism, that's going to have mixed with some of the calcite and cause changes in color. What we do see, though, and what makes them easy to distinguish, is the cleavage or lack of cleavage that is for the minerals. So remember, going back to chapter 3 where we talked about minerals, calcite had very good cleavage. That means that when you break a crystal of calcite, you get a nice flat surface that reflects light. So when you look at marble, you are looking at lots of broken crystals, right? Because you're basically looking at a broken piece of marble. You break it open and what you see are all those flat cleavage surfaces. So it tends to look pretty glittery. Calcite, on the other hand, quartz, on the other hand, did not have cleavage. So when you break a crystal of quartz, it just breaks in a random sort of direction and you don't get those nice flat surfaces. So therefore, you can distinguish these two rocks by comparing them and looking for the one that has the little glitter of the crystals shining back at you, and that one will be the marble instead of the quartzite. This particular non-foliated metamorphic rock is not in your textbook. And we have nice samples of it that you would see if you were on campus. I don't think there are any samples in the sample boxes that you've gotten from eScience. But it's still an important rock, and we're going to talk a little bit about it. So this rock is a little different than the other rocks we've talked about. The temperature is high, and we're talking only confining pressure, so there's no tectonic event involved in this. It's not created during a mountain building event. The grain size can actually vary, can be kind of small to very coarse. It's not microscopically small though. And the mineral composition are some very calcium-rich silicates. And the reason that we get this rock forming is because there are some areas where limestone is the rock at the surface, and then felsic magma will move up into that crustal area and begin to react with those limestones. What happens then is that the heat from the magma drives off carbon dioxide. Remember, calcite is Ca, calcium, CO3. So basically the heat drives this out, and it sort of leaves the area as a gas, and it leaves a lot of calcium behind. And so that calcium gets added to the felsic magma, and that's why we end up with these calcium-rich silicates. The samples that we have and the ones in this picture are often called the Christmas tree rock because they contain red garnets, a calcium-rich garnet, a green calcium-rich pyroxene, and then a white mineral that's called wollastonite. It's very similar to a pyroxene, but not quite the same. And then finally, the last non-foliated metamorphic rock is the rock hornfels. Hornfels is non-foliated again. In this case, it's confining pressure only, so it's not made of a mineral that won't foliate. If you put the parent rock of this through metamorphism with directed pressure, the minerals would foliate. And so that means we're talking about confining pressure only to form this rock. It's relatively fine-grained, and it's usually dark gray in color. There are actually two possible parent rocks. Shale can form a hornfels, and basalt. So in both cases, you'd have to have those rocks being metamorphosed under confining pressure only. When you have shale as the parent rock, you tend to get micas as the mineral in the hornfels. But if you have basalt as the parent rock, then you tend to get mafic minerals within the hornfels. So when you're looking over your own samples in your sample box, the first thing that you really want to try and see is foliation. Now, you are looking at fairly small samples, so I would recommend getting your hand lens out to look at them. And remember that foliation can be the banding, where you could be looking at dark and light bands, so minerals that are different colors, basically white and dark bands on the rock. Or you could be looking at the mica foliation, in which case you want to think about the sides and the top. So if you have a sample, it's obviously not going to be exactly like this, but look to see if there's some place where you can see lots of very fine layering, because that's the indication of the mica foliation. Again, if it's very flat and straight, then it's probably going to be something like a slate. But if it has any kind of a little curve to it, it might be something like a phyllite. Schist will, again, be more shiny. And then when you're looking at the non-foliated samples that you have, remember that glittery versus not glittery for distinguishing between marble and quartzite. I also recommend this particular figure from the textbook, So this has the textures listed here and kind of shown, and I think that can be really helpful when you are trying to identify the samples.